Hi, this is Talk Guo from Vascular Imaging Lab, University of Washington. Today I'm going to present Abstract 24, 3D registration of multi-contrast, multi-timepoint intracranial artery MRI with synthesized vessel maps. Image registration for MRI scans of different time points and different modalities is a fundamental step for clinical application. Firstly, serial scans are commonly used to monitor tumor growth, post-surgery evaluation, regular follow-up reassessment, something like that. This longitudinal scan registration task is still challenging due to the anatomical structure change over time, differences in scan coverage, and all the other possible factors. Additionally, multi-contrast weighted imaging poses additional demands, making registration more complex because of the unclear intensity mapping relationship between different contrasts. In regard to intracranial artery MR imaging, accurate registration of vascular features becomes very critical for advanced vascular applications, where in those cases where small, narrow vessels have to be accurately registered in order to analyze vessel lumen and wall features such as stenosis or plaque. However, existing registration methods, while suited to general and global brain registration, are not optimized for study of the intracranial arteries. So, the purpose of this project is to develop a vessel-based 3D image registration technique for evaluation of intracranial arteries with multi-contrast, multi-timepoint MR images. As arteries only constitute a small number of pixels in these brain scans, and therefore are easily misaligned in a global registration, we take advantage of synthesizing TOF angiography as an estimation of vascularity to achieve vessel attention during registration. This deep learning-based TOF GAN synthesis will help improve the accuracy of multi-contrast, multi-timepoint 3D registration. Generally, TOF MRI represents the vascularity and blood flow information such that lumen is indicated hyperintense while other areas are hyperintense. It is easier and more straightforward to estimate the vessel distribution in TOF than in a black blood MRI like T1 weighted images. With this vascularity ROI estimation, we are trying to penalize the misalignment of those vessel area more than that of surrounding tissues, and so that we can enforce vessel-based registration. Therefore, as shown in this figure, we first estimated a probability distribution of vessels of the reference T1 weighted images by generating TOF using the GAN network. After that, different weights are assigned to vessel and non-vessel areas to measure similarity between the referenced image, that is the T1 weighted image, and the moving images. The registration will be finalized once the optimization algorithm is converged. This workflow is flexible that it can be applied to different types of moving images, that is different types of registration tasks like contrast enhanced T1 weighted PD, TOF, or SNAP in the same scanning sessions, or the other T1 weighted images from another time point of the same patients. The first step of our workflow is TOF angiography synthesis. This proposed unsupervised TOF GAN is aimed at learning a mapping between T1 weighted and TOF domains. There are two branches of the network containing 4 subnetworks, as shown in this figure. Either branch in a symmetric fashion uses UNet as the generator and another 5-layer convolutional neural network with softmax output as the discriminator, which can be optimized with adversarial loss. To ensure TOF generation with high structural similarity and high image quality, we added designed loss to penalize the failure of generating bright pixels which denote vessel areas, so that we use L2 loss, and to penalize those low structure similarity measurement index, so that we use SSIM loss. In this T1 reconstruction branch, we use cycle consistency loss to guarantee unsupervised training, so that we don't require pairwise pre-registration before the training, and to prevent mode collapse. After training, only the first generator is used to synthesize naturally co-registered TOF from T1 weighted images. Second step is vessel-based 3D registration. The probability map of the vessel areas on synthesized TOF are estimated using auto-binary thresholding, where all pixels on TOF are clustered into vessel and non-vessel areas based on intensity. This vessel map is then applied as a weighted attention mask to calculate the similarity metric between fixed, that is T1 weighted images, and moving, that is other contrast and time point images. In our implementation, we sample 50% of points in vessel and 10% points in non-vessel areas, and we optimize matters mutual information to obtain an optimal rigid transformation. We obtained 95 subjects with known symptomatic middle cerebral artery stenosis. All these patients were scanned with TOF MRI T1 weighted pre and post contrast vessel wall images at baseline at 1 year. We use 75 pairs of TOF and T1 weighted images. They don't have to be pre-registered as the training set, 10 as the validation set, and 10 as the test set. We evaluated the performance of both longitudinal registration between pre-contrast T1 weighted of 2 time points, as well as the registration between pre-contrast T1 weighted and other 2 contrasts of the same time points quantitatively. To look at the results, the left image shows an example of our generated TOF from T1. We haven't yet quantitatively evaluated the TOF generation results. This validation and further optimization in training a better state-of-art neural network is a future work. Then to compare the registration results, we calculate the mean DICE score from manually labeled artery regions of all the test sets. That is 0.704 with our synthesized vessel map, and 0.567, that is without our synthesized vessel map. The left images shows another comparison of our registration results. We can see that the artery structures aligns better in the left panel, that is with the vessel map, than in the right panel without the vessel map. The efficacy of this intracranial artery MRI registration can be visualized using this straightened curve NPR view. We obtained the artery center line in this baseline TOF MRI images, and we map these center lines into all the other registered images. The straightened artery here can show that our registration actually works pretty well. That's all for my talk. Thank you. And welcome to questions.